Okay, let's get started. Yeah, first of all, I sent an announcement about a club called Gator Amateur Radio. I'm not sure whether you're interested or not, but it seems to me pretty interesting. So amateur radio is kind of a radio frequency that we can use for experiment and so on. Okay, and Matthew, do you want to say a word on this?
Yeah, I mean, in the announcement that he sent out, there's a couple like flyers. So this weekend we have a field day, which is just like an outdoor operating event. And then on the following Monday, we have a meeting at 7 p.m. in Larson Hall. And we'll just kind of go over what ham radio is and what the club does.
Yeah, I think it's very cool to have this kind of club here. Okay. Yeah, and so I will upload. So lab 0 will be done today, right? And I will send lab 1 very soon. And the lab 1 will cover the material starting from Monday, okay? And then I'll also upload our homework 1, okay? The homework 1 will cover until today. Okay, very good. And yeah, for the last lecture, for the last lecture video, so I uploaded. But I didn't make it public yet, so I will probably do that very soon. So I forgot to turn on the recorder for the last video, so I have to use the sound from the camera, which is pretty bad. So if you watch the video, just bear a little bit, so the sound is not good enough. Yeah, so now I make sure this is turned on. Hopefully it'll be fine. Okay, let's get a brief overview of our last lecture. So in our last lecture, so we covered the decibel notation, and we covered the communication loss, right? So we didn't cover the decibel notation for power yet, so we're going to do that today. Okay, and here is basically the decibel notation. So the reason we use decimal notation is that, so we want to avoid very large and very small numbers, right? So just take a 10 times log 10 of the original number, and then we get a decibel notation. And if we want to convert from dB to linear units, so this is the formula that we're going to use. And those are some common decimal values. Like if we say it's 2, then it means 3 dB. If it's 10, it means 10 dB, right? Those two are very, very commonly used. And here are some examples of dBi and dBd that we talk about, right? Because in practice, especially for antenna design, so we want to see the comparable gains, compared to typical antennas, right? So one typical antenna that we use is this isoradiator. If we compare the gains with this antenna, so that's called dBi. And if we compare the gains with antenna called half-wave dipole, so then the gain is called dBd, and those are the values. And we need to be careful that dB, dBi, dBd, they are not actual unit, right? They don't have a unit, actually. So it's a comparable value. Okay, and then we see an example then how to compute the linear gain from the dB value. And you can take a look at the lecture notes to see the solutions. And then we cover the communication loss, right? So basically, the definition of the communication loss is nothing but the ratio between the transmit power and the receive power, right? And then we take, maybe we can take convert it to the dB domain, right? So that is normally what people do. And because we know the free space Freese equation, right? Then we could compute this value very easily. So this is how we compute it, right? So this is how we compute it from the Freese equation. And we have two cases to consider. So one case is with antenna gain, GT and GR, and the other case is without the antenna gains. Okay, and normally in practice, this without antenna gain case is what we use, right? We just ignore GT and GR, and then have this equation, right? And then we do, after some simplifications, so this is what we get, right? So we have we have a path loss term, right? And we have a frequency loss term, and then we have a constant here. Okay, and from here you can see that the bigger the distance, the worse the loss, right? And the bigger the frequency, and also the worse the loss. Okay, but yeah, that is under the free space model, right? The free equation. So if we have another model, it can be slightly different in practice. Okay, and the other thing I want to emphasize here is that everything we derived so far are based on the assumption that so the loss is proportional, inversely proportional to 1 over d square. Okay, this square is actually not typical in practice. Under the free space model, it is square, but in practice, so this number is normally bigger than 2. Okay, so if it's bigger than 2, the only thing we need to change is that, so we just take this n out. So n basically means that d to the power of n instead of to the power of 2, right? And then, so this is a new formula that we can use, right? So in practice, so this path loss exponent is normally between 2 and 4, okay? And for the millimeter wave communication, like what we use in 5G, this n can be much higher than that, okay? Yeah, any questions so far? Good. All right. And then we talk about the relative power and the path loss. So basically, the meaning of the relative power is that, let's say we know the power at a distance of d0 from the transmitter, and then what is the power that at a distance of d, right? So this is how we do this. So using this the Friese equation, right, and then we can derive the relationship between d and here should be d0. Okay, so d0. It's a typo. Is it? Yeah, it's a typo. Should be d0. Okay, so we derived this relationship in class. Okay, and then after some manipulation, we can see that so the received power at distance d basically equals to the received power at distance d0 minus a term. So this is defined by this, right? So this part is called path loss, right? Because it's a loss due to the distance. Okay, in practice, most likely we'll just pick d0 equals to 1 meter, and then we could compute the received power at distance d, right? Okay, and as we said before, so normally when we say the relative power loss, we say if it's a factor of 2, then it means 3 dB. If it's a factor of 10, it means 10 dB, right? So let's say if we increase the distance by a factor of 2, which is 3 dB, then the path loss will increase 6 dB more, right? Because there's a power square relationship, okay? And then we go over of Voyager 2 example in class, so you can take a look at class notes. Okay, so yeah, I'll just go over the slides because the decibel notation for power is a relatively simple concept. So basically, this basically means that in practice, so when we talk about the transmit and receive power, we also use the decibel notation instead of linear notation most likely. Okay, so for the decibel notation, we have 2 of them. So one is dB watt, and one is dB milliwatt. Okay, and so for the linear notation, so we use the PW to denote the watts and MW to denote the milliwatts, right? And clearly, the relationship between PMW and the PW is 1,000 times, right? So yeah, 1 watt equals to 1,000 milliwatts, basically. And here is the dB notation. We just use the formula that we learned before to transfer it from the linear notation to the dB notation, right? And we use the dBW to denote the dB watts, and use dBm to denote the dB milliwatt, decibel milliwatts, okay? And if you want to see the relationship between the dBm and dBw is via this formula, right? You can see here is the definition, and then we use 1,000 times PW to replace PMW, right? And then break these two, we have this term and add this term, right? This term is a constant, so if you compute it, it equals to 30, right? Because here is 10 to the power of 3. So basically, it means that if we know the dB watt, if we add 30 dB, that will give you the dB milliwatt. Okay, so that's the decibel notation for power. Any questions? Okay, good. So now let's take a look at an example. Yeah, we're gonna solve this equation, this problem. So a CDMA cellular base station operating at 1897 megahertz uses approximately 13 dBW transmit power for each user's channel. The power is transmitted through a directional antenna that has 17 dBi gain. Okay, the key is here is dBi. Remember what is dBi? And the received antenna gain is approximately 3 dB, right? The received antenna gain is just 3 dB, not dBi, not dBd. And neglecting losses, so we don't need to worry about these sentences. Later on, we're gonna learn what are the other losses for the communication, okay? So if we don't have any other losses, so what is the approximate received power at 100 meters and at 10 kilometers, okay? And we need to answer this using the unit of dBm. Okay, that clear? Question? Right, so basically, it asks you to receive power at 100 meters, right? Let's solve the first part first, okay? So what should we do? Right, so far pretty much for this kind of problem, we just learned one equation, right? Everything else was derived from that equation, okay? So the equation is the free space equation, right? So let's write it down. So basically, we know the received power, PR, PRD equals to what? The transmit power times the transmit antenna gain, receive antenna gain, lambda square over what? 4 pi d square, right? So this is pretty much the most fundamental equation that we have learned so far, okay? And yeah, let's see. So basically, our goal is to compute this guy, right? The only thing we need to check is whether we know all of these terms here, right? If we know all of them, then we're fine, okay? Let's see whether we know that or not. So first of all, PT. So what is PT? The transmit power, right? So what is the transmit power? Is this value, right? 13 dBW, right? So we know that. So the transmit power is 13 dBW. Right, normally when we compute that, we can use the dB unit or use the linear unit. Use the one that you prefer, okay? So here, so I feel more comfortable to use the linear unit. I will just convert everything to a linear unit and then convert everything back to dBm, okay? So this is how I do this. So basically 13 dBW is nothing but 10 to the power of 13 divided by 10, right? It's 10 to the power of 1.3 watts, right? So that is approximately 20 watts. Okay, so we know PT, and then let's see GT. So what is GT? Yes?
17.
Very good. 17 dBi, right? And remember, dBi is to compare to SO radiator. SO radiator basically means that their GT is 1, right? So basically, that is nothing but 10 to the power of 17 divided by 10, right? 17 divided by 1 divided by 10, so this 1 doesn't matter. So we have this, so it's 10 to the power of 1 minus 7, so that is, roughly speaking, 50. Okay, so it's unitless. We don't have a unit for that. So this is the transmit antenna gain, and then how about GR? So what is GR? Yes? 3 dB, yeah. Very good. So GR is 3 dB, so basically then we have, so that's 10 to the power of 3 divided by 10, right? But it's 3 dB, right? So we know what 3 dB is. So it's just a factor of 2, right? Okay, very good. Okay, so next value is lambda. Let's see whether we know lambda or not. Do we know lambda? Yes?
We know the frequency and the speed of light. So.
Very good, right? So basically, lambda equals to C over F, right? And we know C and we know F, right? F is 1897 megahertz, so let's compute it. C is 3 times to the power of 8, And then, so the frequency is 8097 times 10 to the power of 6, right? Because it's mega. So then that equals to 3 divided by 18.97, right? We cancel 10 to the power of 8, and then we get 0.158. So the unit of that is meters. Okay, so that's lambda. So we'll almost get everything, right? Okay, great. And then we just compute. Now we have everything, right? So D, we have to plug 100 meters in, and we have to plug 10 kilometers in, and that's it. Okay, yes?
For GT, you said something about 17 divided by 1. Could you explain that?
Oh, because so the unit here is dBi, right? So basically, so this GT means that maybe I'll write it this way. So the GT, I'll use a prime for our antenna divided by the GT. I'll say GTI, so that's for ISO radiator. Okay, so GTI basically means the gain compared to that antenna. It's a ratio. Okay, since in this case, this guy equals to 1, then our GT basically, this I doesn't matter. Okay, so basically every time we'll see there's an I here, so you should be happy because it doesn't matter. So that's basically, that's the gain. Does that make sense? Okay, great. Okay, so then we just compute everything, right? So I will just ignore the computation process because we get everything. We just plug everything in, right? And so at a distance of 100 meters. And in this case, you can see this number would be 3.2 multiplied 10 to the power of minus 5 watts. Okay, so the next step is that we want to convert it into dBm. Okay, so into, let's say, yeah, maybe we convert that to dBW first and then convert it to dBm. So this equals to 10 log 10, and we plug this number here, right? If you compute that, you're gonna get this, so that is minus 45 dBW. Okay, then if we convert that to dBm, so remember what we just learned, right? We just need to add 30 on top of it to get the value of dBm. Minus 45 plus 30, so that's minus 15 dBm. Okay, so that's how we solve the problem. So any questions? Yeah, and for the other case, so you can see my notes, right? We just use the same procedure and then use another number of 10 kilometers here, and you'll see that, right? So clearly, it's we just need to use a different ratio here, right? The first number will not change, right? Okay, and that is what we left from the last lecture. So any questions? Okay, so now we're pretty much finished the first part. Okay, and from now on, oh yeah. Let me open this. And from now on, so we're going to do some reviews of your signals and the system class. Right? Did you take signal system? Everyone, right? Okay, great. So yeah, I will not write anything in particular here because those are just reviews, right? So in this lecture, probably the next two lecture, so we're going to review the basic concept of signal system, including what are the signals, right? What are the systems, what are convolution, and all the Fourier series, Fourier transform. Okay, and that the lab one is about that as well. Okay, and here are outlines of this lecture, right? We're gonna go this very fast, right? And if you have any question, just stop me, okay? And we finished the decimal notation for power already, and then I will just cover what is a complex number. So all of you should know what complex number is, right? Because you learned signal system before. So, and then I will give you the definition of the inner product and norms, and then we're going to talk about signals and time averages, like what are the energy of the power, what are the energy of the system, and what is the power of a signal. Okay, not system, a signal. And then I'll cover 3 special functions, right? So like the most basic special functions in your signals and system class. Okay, let's see what are they. Okay, first of all, complex numbers. Oh, by the way, so did you take complex analysis? It doesn't matter, so we don't need that deep concept, just wondering. Okay, great. Yeah, for a complex number, so we have 2 forms. So one is Cartesian form, and the other is polar form, right? So for the Cartesian form, it's defined by x plus jy, right? And maybe I can use, yeah. So for j, it's defined by the square root of -1. Okay, so this is the definition of the complex number. And we have, so r is the real part, and m is the imaginary part. Okay, and then, so we have 2 forms. So one is Cartesian form, and one is polar form, right? So Cartesian form is in the form of x plus jy, and the polar form is in this notation, right? In figure, so if we draw a complex plane, so x-axis is the real part, and the y-axis is the imaginary part. And the coordinates is basically the Cartesian form, right? So x plus jy, x, y are the coordinates. Okay, and for the polar form, so we consider that as a polar plane, right? And r is basically the radius, right? So here is x, y, and this is r, right? The radius, r, and this angle is basically the angle or the face of a complex number. Is that clear? Okay, so maybe think about one question, right? So how to compute the angle or the face of a complex number? How can we compute that? Yes?
Use arctangent.
Arctangent? Any different answers? Everybody agrees? Yeah, almost, right? Half of them is correct. So one reason is that, so basically the angle is from 0 to 36 degrees, or from 0 to 2 pi. Okay, it's a round. Okay, how about arctangent? You mean arctangent y over x, right? Yeah, how about arctangent? What's the range of arctangent? Yes. Are your no? Okay. Okay. Yeah. Yes. Arctangent. Almost, right? It's from negative pi over 2 to positive pi over 2, right? So it's just half of the plane, right? The other half was not covered, right? How can we see the other half? We just need to add or minus pi, right? Depending on where the number is, right? Just be careful on that, right? So when we compute the phase or the angle, it can be very tricky. Okay, very good. And conversions. So obviously we have a relationship between the Cartesian form and the polar form, right? First of all, they are definitely equal. And when we want to compute the magnitude or the r, so this is the formula we use, right? Square root of x squared plus y squared, right? And clearly x equals to x times cosine of the angle, and y equals to r times sine of the angle, right? And how to compute the angle here, right? This can be tricky. We need to be careful. Okay, so why we want 2 forms, right? So why one form is not enough, right? The reason is, one of the reasons is the ease of the computation, right? For example, if I want to do an addition of 2 complex numbers, right? We just use the Cartesian form, it's better because we just add the real part and add the imaginary part, and then we get the result, right? For addition, the Cartesian form can be better. And for multiplication, we can see that, so if we use the Cartesian form, then we have to compute in this way, right? So kind of complicated, but if you use the polar form, it's very easy. So if we want to compute a division here, a multiplication here, so we just need to use the multiplication of the magnitude, and here we just add a phase or add the angle, then it'll be done, right? It's kind of easy to use the polar coordinates for the multiplication and the divisions. Okay, and another basic operation for complex numbers is conjugate, right? So this is what we're going to use all the time. So by the definition of the conjugate, in the Cartesian form, we just need to change this sign from plus to minus. And for the polar form, we just need to add a minus sign in front of the face or the angle. Okay, so that's the basic operation of the complex numbers. Okay, and any questions so far? Okay, yeah, you have seen that before. Next is, so now with the knowledge of complex numbers, so now we turn to complex signals, right? The complex signal is just complex functions, right? So the name of the complex coming from the fact that the signal can be complex, right? It can have a real part and the imaginary part. Okay, and for the definition of the inner product of two functions, so this is the definition. Okay, so basically f multiply g conjugate, and then we do an integral. So that's the inner product. Okay, for a function. And let's say if we maybe do some sampling, right? So we have two vectors here. Okay, and then so they are basically the same operation, but here since we have different, it's a vector instead of continuous function, and then we just do a summation instead of an integral here. Okay, so this is the definition of the inner product for the complex vectors. Okay, questions? Good. All right. Yeah, and the definition of norm here is basically to compute the inner product of f with itself. Okay, so if g equals to f, so basically this is the definition of the norm, right? The inner product between f and itself. Okay, and in particular for the complex signals, so this would be the definition, right? Before it is g, now we have f here, and this is basically the definition. Okay, so we're going to see how we apply that in a minute. And for vectors, so again, so we're going to use the previous formula again. So instead of g, we have f here, and then we just do a summation instead of integral because now it is vectors. Okay, for signal system, you can see basically for these two cases, so this will apply to the continuous time case, and this will apply for the discrete time case. Okay. And the next concept is orthogonality, right? Let's say if the inner product of the two functions equal to 0, then we say these two functions are orthogonal to each other. Okay. Any questions? So did you see this before? Right, for everyone? Yeah, great. Okay, so now let's see signals and time averages. So first, we have to see some classification of signals. Okay, there are so many ways to classify signals, right, in your signal and system class. So can you illustrate some? So here, what I'm talking about, what I will talk about is the energy and the power signal. So what are the other kind of classifications of signals that I can remember? Yeah, one is continuous time signals and discrete time signals, right? Are there any other types of signals?
Periodic.
Very good, right? Periodic signals that we're gonna talk a little bit, and then non-periodic signals, right? Yeah, very good. Okay, so anything else? Yes?
There's like finite power, finite energy.
Yeah,
Those are different, right?
very good. Yeah, that is what I'm going to talk about now. Yeah, there are like other types of signal. For example, we don't distinguish that a lot, but in practice there's a tiny difference, right? Did you heard of the analog signal and the digital signal? Right. So theoretically speaking, or precisely speaking, so that is different from the continuous time and the discrete time signal, right? So normally when we talk about continuous time signal or discrete time, so we mean the x-axis, right? They're continuous or discrete, okay? But when we talk about the value of the signal, yeah, they're analog or digital, something like that, right? Sometimes we don't distinguish, sometimes we do. Okay, very good. Now let's go back. Let's see what is the energy of signal, right? So here, basically, the energy of signal is nothing but a norm of a signal, okay? So this is the definition here. So we just do a norm, and then we do an integral, okay? Not do a norm, do a square, and then do the integral. So that's basically the energy of a signal, right? Yeah, this is just a definition, right? I think this is from the the circuit, right? The real energy should be if it's a voltage, then we need to have a resistance in the downstairs, right? If it's a current, then we will multiply with the resistance as well, right? So this is from there. Okay, and if GT is a real signal, then we don't need this absolute value anymore. We just use this equation to compute the energy. And here's very important. So let's say if the energy exists, right, it's less than infinity, then we say G of t is an energy signal. Okay, and I didn't write it, but normally we consider E of G is bigger than 0 as well. Right? Think about for what kind of signal then the energy is 0. Right, so basically if this guy equal to 0, then what GT will look like? It's just 0, right? And we don't care, I mean 0 means nothing, right? We don't care those kind of signal, right? Therefore, normally we also assume E of G is bigger than 0, okay? Okay, and here are some examples of energy signal, right? So basically, for energy signal, in order to make this integral finite, so one possibility is that if we have finite magnitude, finite amplitude, and finite duration, for sure the signal would be energy, right? Finite magnitude, finite duration, right? And here is an example. It's a rectangle signal. Clearly, we can compute the energy of it, right? But that is not necessary, right? So for example, let's say if for a signal that have infinite duration, right, like this, so it's an exponential signal, right? Let's say if, so it's decaying, right? If it decay all the time, although it will last forever, so if we compute the energy of it, so it's still finite, okay? So for energy signal, the time duration doesn't have to be finite. Is that clear? Similarly, right, for the amplitude, it also doesn't have to be finite, right? With a similar idea, right, for example, for this kind of energy, for this kind of signal, let's say for this signal, if x approaches to 0, then it will go to infinity, right? But for this kind of signal, if we do compute the energy, and so this is what we get. It's 2, so that's finite. Therefore, this signal is still energy signal, right? So any questions? Okay, great. And so now let's see. So what about energy is not 0, it's infinity? Okay. So when the energy is infinity, so the most important kind of signal that we care about, especially for signal processing or signal system, is the periodic signal, like sine, cosine, and so on, right? And here we consider a signal of sine 2 pi t, and if we compute the energy of this signal, right? So basically, we divide the whole integral into an integral for each period, right? Or each fundamental period, and then we can compute this, and you can see that. So the energy for each period is half, but the summation is over minus infinity, from minus infinity to plus infinity. Then clearly, the energy of a periodic signal like this is infinity. Okay, so the energy does not exist, right? But we still want some description in this kind of metric, right? Because so the reason we use energy is that it's a very simple one-number metric, and it can tell you something about the signal, okay? But for this kind of signal, can we still use this kind of metric, right? But modify the definition a little bit. Right, we can, right? Because so although the energy from the entire time horizon does not exist, but the energy for each period cannot exist, right? And this can also tells you something about the property of the signal, okay? So with this idea in mind, we introduce the concept of power, right? So basically, the definition of power is average energy, right? You just compute the energy, and then we divide it by the time duration, and let the time duration go to infinity. Okay, so that's the definition of the power of the signal. Yeah, that clear? Right, kind of boring, right? So I'll quickly go over all the concepts here. Okay, and okay, so basically, for the power signal, we still need to worry about the existence of power, right? Because the power does not exist all the time, okay? So one typical signal that we care about power and we can compute its power is a signal that we have seen before. It's a periodic signal, okay? So what is a periodic signal? Intuitively?
Signal that repeats.
Very good. The signal repeats itself, so basically. But one important definition for a periodic signal here is that the signal has to repeat itself forever, right? If it just repeat and then stop, then it's not periodic, right? So it has to repeat forever. That's extremely important. And so we can see from here, right? T has to in R, right? Basically, T has to from negative infinity to plus infinity, right? So this is just a mathematical concept, right? But in communication, this is extremely, extremely important. When we are towards the end of the class, when we learn OFDM, right? So all the concept there depends on this, right? Depends on it has to traverse the entire horizon to make the system work ideally. Okay, that's very important. It's very important. And when the signal is periodic, then actually we don't need to use a formula we introduced before to compute the power, right? Because this formula is kind of complicated. So we need to compute this guy first and then let t go to infinity to compute the power, right? Which is a two-step process, right? But if a signal is periodic, it's a one-step process. So we get rid of the limit, right? So we just need to do the integral over one period. So the period can be any period, right? Just pick the one that you like, from 0 to 2 pi, from minus pi to pi, doesn't matter. Okay, and then you normalize it by the length of the period, right? So this period doesn't have to be the fundamental period, okay, or the smallest period. It can be any period, right? Then it will work. And the other type of signal is the random signal, right? For random signal, we can also compute this kind of property. So, but we just ignore that here. And when we talk about random signal, so we can discuss that again. All right, and we say, okay, similar to the energy signal, right? So we say when the power exists, so it's bigger than 0 or less than infinity, then we say the signal is a power signal. Okay, so P of G has to be less than infinity, so that's very easy to understand. So why we need PG bigger than 0? So what if PG is 0?
Then the signal is just 0 like before?
No, not really, because here we normalize it by the time horizon, right? So this signal doesn't have to be 0 to make the power equal to 0. Think about energy signal, right? So what is the power for an energy signal? Yeah, the definition of an energy signal is nothing but we do this operation, but the integral here is from minus infinity to plus infinity, right? That's the energy, right? If you compute the power for an energy signal, what that would be?
Just like the average of a piece of the signal?
Not really, right? Think about if we have an energy signal that have finite time duration and finite amplitude, right? Like a triangle. Okay, if we do an integral of it, right, it's kind of the area of this signal, which is finite. So if we normalize it by the time horizon, and then the time has to go to infinity. So the power would be 0. That make sense? That makes sense? All right, just try it on your own, right? Compute, let's say, let's say if we have a signal like this, first, let's say we have, yeah, just consider this kind of signal g of t, right? Compute the energy of it, right? 1 square is just 1, right? The energy of this signal is nothing but this area, which is 1, right? And then if we use this formula to compute it, right? So this guy, if we make t large enough, so this guy will be 1, and we divide it by t, it will be just 0, because t has to go to infinity. Does that make sense? Right? Okay, so basically we can see that for all the energy signal, the power will be 0. Okay, so that's why we need PG should be bigger than 0, because when PG equals to 0, it's energy signal, right? So because this is kind of like a classification of signals, right? So one signal has to be either energy or power. We don't want a signal that is both energy and power, right? Otherwise, why want to do this? Does that make sense? Okay, yeah, that's basically the definition of power signal. And the other thing is that, so in reality, we don't have infinite time horizon, right? For example, if I want to transmit the signal, right, it has to stop at some point, right? It cannot last forever, right? So in practice, all the signal is energy. There's no power signal in practice, right? Because no one can live forever, right? To see the signal will last forever, right? But so why we still want to, study power signal, right? So why we still want to study periodic signal? Right, there are many reasons for that. So one reason is that the periodic signal is very easy to analyze, and that can be seen from the Fourier analysis, right? All the theory of Fourier analysis based on periodic signals, sine and cosine, right? And as I said, right, in the later part of the class, you'll see in practice, we may have a very cool technique to make sure that although the signal is not periodic, and it doesn't look like periodic, but by using some cool mathematical technique, we can still make the system work as if it is periodic. Okay, but we need to understand the property of the periodic signal first. Okay, so this kind of signal is very, very useful, right? Yes?
It's kind of like how, like, in a typical sense, there's, like, in the engineering world, it's like the ideal scenario, it's the easiest way to do math and calculate things, and you actually apply it. So like, power signals is like that, versus energy is the actual realistic thing that you're using.
Very good. Yeah, this is one idea, I would say, right? It's definitely part of the reason. But the cool thing here is that for telecommunication, it's kind of pretty unique, right? Normally we say, okay, so in practice, we don't have infinite time horizon, right? What if we just have a sine signal, right? It lasts really long, right? Because frequency is extremely high, and if we see, for example, let's say for 3G signal, the frequency is like 1897 megahertz. It means that for 1 second, it have 1897 mega periods, right? It seems a lot, right? Let's say if we observe it for 1 minute, it almost looks like infinite horizon, right? But what I'm saying is more than that, right? It's not approximation. So we can use this idea to get some exact things that we can get for periodic signal. Yeah, that's really, really cool, right? But what you said is definitely part of the reason. Okay, very good. Okay, yeah, this is just another very useful formula. So in practice, so when we compute that for a signal, right, without the square, okay, so this is the DC component, right? Meaning something doesn't change. We just average the the changing part out and get something that is not changing. Okay. In practice, especially for communication system, we don't want this guy to be non-zero. We want this guy to be always 0 because DC part consume energy. Okay. Very good. Okay, so now let's see the last part. So that are special functions. Okay, so in signal system and in the telecommunication system, so we have 3 functions that are most important that we use all the time. So one function is complex exponential, right? That looks like this, e to the power of j omega t. So by using the Euler formula, so that equals to cosine omega t plus j times sine omega t. Okay, so who have seen this before? Yeah, because you have seen for signal system, right? So yeah, all the theory analysis will be based on the complex exponential signals, right, in telecommunication system. It's very important. And for this kind of signal, we could, because so it is just a complex number, right? Because it's a function of t, then we just write in this way, and we could compute the magnitude, and we can compute the phase. Okay, and this is the phase equation. Okay, so let me know if you have trouble to understand what does that mean. Okay, and some properties of the complex exponential, because this equals to cosine plus sine. J is just a constant here. Okay, therefore, so this is a periodic signal, this is a periodic signal, then the whole thing is a periodic signal. Okay, and the fundamental period of this is 2 pi over omega. So the fundamental period basically means the smallest period of a signal. Okay, and we can show that. So for the complex exponential, it's a power signal, and it's non-causal signal. So non-causal signal basically means that there are some parts for the t less than 0, right? If the signal is 0 for t less than 0, then it means it's a causal signal, right? So for this signal, because it traverses to everywhere, so it's a causal signal. And just to emphasize a little bit for the Euler's formula and the relationships, so this is the relationship between cosine sine and the complex exponential, right? We use this formula to get cosine, and we use that to get sine. Okay, and so is that clear? Right, just use the definition, then you can see it. And then, so e to the power of j pi is -1, right? Because cosine pi plus j times sine pi, so that's equal to -1. And therefore, if we use -1 to the power of n, so it just, because it's an exponential, right, that equals to e to the power of j pi, nj pi. Right, that's a kind of a trick that we may use when we do computation. Okay, so the next one is the direct delta function, or the direct delta signal. Okay, so that's defined in this way. So when t is not 0, so this is 0, and when t is 0, so that's tricky, right? When t is 0, delta give you infinity basically, but it's not just any infinity. So if we do an integral of delta here, so this will give you a 1. Right? By the way, so although we write integral here, so that cannot be the Riemann integral that we learn in the calculus. It has to be some other type of integral. Okay, so kind of very tricky definition, but the idea is not that tricky. So basically, this is the idea, right? So in practice, we want to express something that is really big in the 0, but almost nothing everywhere else, right? So this is a mathematical abstraction of this kind of signal, right? In practice, it could be something like this, right? It's a rectangle signal, but we keep the area the same, which is 1, and then we let the width of it goes to 0, and then the height of that goes to infinity, right? Just a very big peak, okay? And the delta can be approximated by this kind of signal, and now can be also approximated by a rectangle here, right? As long as the area is the same, when this goes to 0 and then the peak goes to infinity, then we're fine. Okay, so that's the idea of delta. Okay, but the mathematical computation can be a little bit tricky. And for the discrete time case, it will be much easier, right? By the way, for the discrete time signal, so it basically means that all the signals are defined on the integer point, right? Not fractions, integer points. n equals to all integers, right? Plus and minus. And for the discrete time, we have a Kronecker delta signal instead of the direct delta signal. So definition of that is very simple, right? So it's 0 when n is not 0, but it's 1 at n equals to 0. Okay, so definition of that is much cleaner compared to that for the continuous time case. And here are some important properties for delta signal. So one property is a scaling property. If we use a constant multiply delta function here, and then do the integral, so basically you're going to get this constant. So if constant is 1, then that's the definition, right? And so normally, we cannot see a value of, we cannot say that C is the value of this guy, right? So normally we just say, okay, so C is the weight of C times delta T, okay? And the other property here is a multiplication property. If we use GT times delta T, so that equals G0 times delta T, right? So that's kind of not very hard to understand or over time. Yeah, I'll just have one slide to show you. So basically, if I have a GT here, and then we use this multiply the delta, so which has a peak in the middle, and then we can see that only this point will be left and everything else will be 0. Okay, so that's basically the idea. And using this idea, so we can shift it by t, right, unit. Now with this idea, we got a very important property, so that's called the sampling or shifting property. Okay, so what it does is that if we use g of t multiply delta t minus a t, do the integral, and then what we get is g of capital T. It's kind of sample one point out of a function. Okay, so this is a mathematical way to do that. Okay, how to get a point from any signal, and then we use the delta function to do the sampling, right? To do this integral. Okay, that is very, very important. So basically, that's a key property to derive convolution that we're going to see later. Okay, and lastly, so this is unit step function. So it's nothing but if t is bigger than or equal to 0, have 1 and 0 for the other side. Okay, and for this kind of signal, we can show that if we do an integral of delta signal, and then we can get u of t. And if we do a derivative of u of t, then we get back of delta t. Okay, and we're going to use that all the time as well. Yeah, and those are the special functions or signals that we're going to use in our class. Okay, and that'll be it. Thank you.